portion.
First things first. Midterm. I promised you one of these.
Wait, we have one?
Yeah. Is, I think, Wednesday, day before Thanksgiving, right?
Oh, gosh.
This quarter's really weird because there's only 1 week of classes after Thanksgiving this year. It's really weird, and finals week is incredibly early. So when we started looking at it, this is the only day we can do it. Besides, this will let me get it graded over which is my job, right, after you take it. This will let me get it graded. Now, what I do is the following with the midterm, right? What I do is the following, is I will give you a sample midterm, all right, on the Wednesday before this. So a week before, I will put out on the web a sample midterm, which will be remarkably like the midterm you have, okay? Remarkably like it, all right? And which means there might be one extra question, or the numbers will change. It won't be exactly the same, of course, okay? But I will get, this is, I treat midterms as not, the university thinks of them as an evaluation device. I don't. I think of them as a learning tool to make you go over the material one more time, right? And so I will give you out this midterm, this sample midterm on the, so it's the 18th, right? And you can look at it. We will hold, that Friday before the midterm, we will hold discussion. So you can jump on Sebastian and ask him, how do you answer this question, how do you answer that question, etc. Okay? And what I want you to do is, you should find, it's not, I don't give really hard midterms, okay? But you should find that it's something you can do. And but I've got to give you one. The university requires it of me that I give you an exam, and so I will give you this midterm, and it will be on the 25th. And afterwards, you can all go home. But the more we looked at this quarter, it's very unusual. Question? No, just spinning your pen. Okay. I'm like an auctioneer up here. Anybody raises their hand. So that's the first thing. And I'll give you out a sample. Print it out. Work it out. Right. 1 year. I tell all my students this. 1 year. I gave out the sample exam. And then I came in, I'd been out of town and I flew in late the night before. I came in the next morning, and all of a sudden it was like, oh, I'm supposed to have a midterm today, ready for the students. And it was like half an hour before class. So I went in Microsoft Word, I edited out sample midterm. I edited the sample out of the sample midterm, right? Just printed it out as fast as I could out the high-speed printer, stapled them up as fast as I could, came into class, and gave out the exact same midterm as I gave out before. And you would think the scores would be incredibly high. It was remarkable to find out they weren't incredibly high, okay? That a lot of the people didn't do the sample midterm. Now, do the sample midterm, right? It's like a homework assignment, and you'll be okay, all right?
Are you going to post a key for the sample midterm?
No, of course not. No. Because then I'll get the exact same questions back. Right. I'll warn you when I give out the midterm, too, that some of the numbers have changed, okay? Do not just repeat what you've done on the sample midterm here, right? Some of the numbers have changed slightly. And so, but you'll see. And so I'm going to give you out a sample. Go over it, work it over, make sure you know how to do everything, okay, and you should be fine. Question?
Are we going to need a Scantron Blue Book calculator?
You will not even need any paper. Ken will supply all the paper. Okay? So you need a pencil, cell phones off, whatever. And if you're using a calculator on one of Ken's exams, you're doing the wrong thing. Bells, whistles, everything should flash, okay? That you're doing the wrong thing if you're using a calculator. That's not what I'm looking for. So everything okay with that? Okay, today I'm going to start discussing subdivision surfaces. Textures yet that much, some of you, right? But virtually everything is there for you to draw pictures within graphics. And now what we need to do is we need to go a little bit farther and figure out how to do some things that you couldn't do normally. And what happens now is that all of a sudden you start running up against data structures problems. And you've got to create data structures for things. Most of us graphics people think of ourselves as really doing advanced data structures. We do this so much. We invent new data structures for things. And with subdivision surfaces, people knew about these things in like 1977. And Chaikin's talk was in like 74 or so. And Chaikin's was the first kind of proposal for this. And once we knew about them, it was like, okay, can't use those, and I'll show you why. Okay, they basically, the machines we had in those days could not handle these things. And only until about the mid-90s did all of a sudden subdivision surfaces came back. And they started being used, okay, early 90s, mid-90s. And they started being used. And so I'll show you kind of the strategy behind subdivision surfaces. We can use them a lot for different things. And then that'll kind of be today. And then on Friday, what I'll do is on Monday, what I'll do is show you what we call the Catmull-Clark surface. Again, Catmull is CEO of Pixar. Clark is started $3 billion companies. I mean, it's two fairly famous people. But we'll show you some Catmull-Clark surfaces and what you can do with those. And those are kind of the standard that people use these days, are the Catmull-Clark surfaces. There's some other ones too. But subdivision tends to be something that you can almost explain to a sixth grader. Right, until you start getting into how do I store these on a computer and things like this. So let me start through this and we'll go. So the first one with Chaikin's curve. And about 1974. And everybody knows this right, by now. You guys all have done this. Basically, it's the 1/4, 3/4 algorithm. Okay? It's the 1/4, 3/4 algorithm, and then you connect the dots. All right? 1/4, 3/4, connect the dots. 1/4, 3/4, connect the dots. Right? And off you go. Okay? And this algorithm is actually not too hard to describe. I'll show you some things on this algorithm as we go next time. But it's actually fairly easy to implement, this algorithm. But what it gives you, we all figured out eventually, what it gives you is it gives you these quadratic pieces, when you're done, that each one of these guys is a parabola. And what it really does is in the end, it pieces together parabolic pieces, right, to get you a curve. And those curves aren't really as good as we would like, because parabolas don't have inflection points. And if you want inflection points in a Chaikin's curve, there's only one place you can have them, and that's where they join the parabolic pieces together. Because you could have one parabolic piece like this and the other parabolic piece like this, and you basically get an inflection point in here. Okay? And so Chaikin's curves are really cool. I mean, they're really easy to define and all. But they have some pretty bad restrictions that come with them. And what we'd like to do is we'd like to lift them up and do different things with them. Okay? And there is a Chaikin surface here. That can be done. And this was really called, in the trade, it's called a Dew and Sabin surface. Because Dew and Sabin kind of did it independently, published it first. Chaikin never published it. But it's a pretty straightforward extension of Chaikin's algorithm. And Dew and Sabin did something cool that other people realized. Something cool about this that other people didn't do is that normally we think of quads on our surfaces, like Bezier patches and things like this. Dew and Sabin realized you could do it on things that weren't quads. Okay? And you could do almost the same type of rules. Now let's see, Malcolm Sabin was a famous sort of engineer in the aeronautical industry in England, and had a university appointment also, and then Donald Dew was his graduate student, and has kind of disappeared, right, ever since this paper was out. But here we go. The idea of this is similar to a Bezier patch, okay? It's similar to a Bezier patch. Okay, and it goes something like this. If you have this array of control points, well, how do you do Chaikin's type algorithm on an array of control points like this? Right? And the idea is, you can probably work this out yourself. What you do is you do the 1/4, 3/4 all in one direction, okay? And then you do it again. It's going to get messy here, folks. Actually, do I have colored chalk? No. Okay? So it's going to get messy. All right? You do the 1/4, 3/4 algorithm here, right? On each one of these line segments in one direction. So let's assume this is the U direction, that's the V direction here. Okay? And now you connect all these dots. Like this, and then you do the 1/4, 3/4 algorithm in the other direction, okay? Getting maybe circles here. And you do them on these lines. Okay, like that. And then what you do with these guys, it's going to get messy, okay, is you connect them up. And you connect them up into squares. These squares are obvious. But you also connect them up across here into squares. It gets messy. Okay, and now after all that, so you've done 1/4, 3/4 this direction, then you do 1/4, 3/4 that direction. Okay, and after that you have these circle points that are all linked up into a new mesh. Okay? And they provide your second mesh. Now what do? Do it again. You 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 get smaller and smaller little quads as you go along. Can you see how you'd extend Chaikin's upward? Okay? And it works nicely. Okay? So you take this mesh, you get a bigger mesh out. If you look at this, Chaikin's kind of expands the number of points you. If you had 3 line segments here, you've got what? 1, 2, 3, 4, 5. It effectively doubles the number of line segments each time you do it, right? So here, it takes the number of squares you have and effectively doubles in one direction and effectively doubles in another. Right? So it effectively quadruples the number of squares you have, right, when you're done. So it goes up by power 4. Kind of. Not exactly a power 4, a little less than that, but go ahead.
Kind of one question and another, depending on the answer. So just to simplify it from the left side, we have, where does the curve actually start?
Here, it starts at the, on the left side here. It starts at the halfway point.
It doesn't start on the x.
Doesn't start on the end.
X.
On the x. No, it doesn't start here. Because what happens is, when you do Chaikin's again, 1/4, 3/4 on this segment.
But I'm saying after one time.
After one time, it starts on the x, right?
So it always chops off the
ends.
Yeah.
Yeah, it always chops off the ends, okay? Unless you, a lot of you I noticed specifically kept the ends running around. And a lot of us do that. Here, it shrinks, right? The thing shrinks down a little bit. Okay, we'll show you how to not shrink eventually. But it shrinks down a little bit, okay? By the way, one of the things with Chaikin's curves is that quite frequently we give Chaikin's curve a polygon, okay? And you have it do 1/4, 3/4 on everything. And you make all the line segments connected to get another polygon. So if it's a closed shape, right, you do it this way, you don't worry about the endpoint so much. You make this last connection, okay? You don't worry about and so you can keep getting this down. There was some question when Chaikin first put this out is, can you get a circle out of this? And the answer is, mathematically, no, you can't, okay? Because what you get is you get parabolic segments, right, which are quadratics. You cannot write a circle as a quadratic, ever. Sines and cosines, okay, to make up circles. And so you can't ever get a circle this way. You can get close, really close, but you can't ever really get one, okay? But so we do this. And similarly here, quite frequently we make closed things, right? And that way it shrinks, but we don't, it moves away from the corner. It still shrinks, though. But can you see how this is going to work? Okay. Now, if I go over here and I look at one of those squares, okay, what I get is these original 4 points here. Something like, maybe I'll label them like that. Okay. If you look in there, what I effectively get is 4 of these Chaikin's points. One there, one there, one there, one there. Okay. I effectively get 4 of these Chaikin points. And I know that any point in here, if this is something that's called bilinear, something called a bilinear patch, TCH, that any point in here, P of U and V, is equal to 1 minus U times 1 minus V times P 0, 0, plus, I hope I get this right, U times 1 minus V times P 1, 0, plus V times 1 minus U P1, 1, plus UV P 0, 1, UV P1, 1. Turns out I can write any point in this patch. Now I'm going to think this is a 3-dimensional picture, right? So my 4 points can be kind of not planar. So the 4 points could be not planar. Turns out I can write any of these, right? Any point in here in this form. Right, now if you, let's see if this actually makes some sense here, that I'm going to say that I guess U maybe is in this direction. Don't write this down yet, I may change this. Okay, and V is in this direction. If I let V be 0 here, that's a 1, that goes away, this goes away, right? These guys go away. And this is a 1 and that's a 1. So I'm 1 minus U times P0, 0 plus U times P1, 0. Right? That's a point on this line. Right? 1 minus U and U. That's an affine combination of these two. It's a point on this line. If I let U be, let's let U be 1, for example. If I let U be 1, this is a 0. That's a 0. And so I get 1 minus V times P1, 0 plus V times P1, 1. That's a point on this line. Right? And what we get is bilinear. That what it means is that all of the lines on the outside here are linear. Okay? And then I can parameterize any point on the inside kind of as this, think of a bubble connecting these things, a bubble surface connecting these things. It's not quite right, but the things on the inside, they can be kind of, you know, funny, u times v, okay, to get these things in. And what you can do is if you run through this algorithm, and it takes, page and a half or 2 pages of a yellow sheet of paper writing equations, you write down the 1/4, 3/4, and 1/4, 3/4, you'll find out that this point here, right, is p of a 1/4 and a 1/4. It comes out. This point up here is p of a 1/4 and 3/4. This point right here is p of 3/4 and 1/4. And this point up here is p of 3/4, 3/4. Okay? With this function p. Okay, now I'm not going to write out all the algebra for this, okay? But this is exactly what you might expect to happen, okay? Is that this comes out. And so we can calculate even the Chaikin's points here within one of these squares. Given one of these squares, we can calculate the Chaikin's points here from this funny equation right away. Okay? But there's more, okay, coming. All right, so now maybe you could see how you could implement a Chaikin's patch algorithm, right? That for each one of your, if you had an n by n array of points, you would make an array that has even more points in it, and you could fill them up just by calculating these points inside, okay, and get these out. Now, what these are really doing here, these guys, if you notice, this is another one of those funny affine combinations that it takes 4 points, and the coefficients out in front all add up to 1. Okay? Let's see, there's a uv there, there's a minus uv there, a minus uv there, and a uv there. All the uv's go away. All right? The only thing left is when you multiply this all out is the 1 when you add them all up. Right? That all these coefficients here add up to 1. So it's one of those funny affine combinations, okay, that you get. And so, moral of the story is we can calculate all these points. And what Du and Sabin did, let's see, did I say everything I wanted to say? Sort of. What Du and Sabin did is they said, aha, look at this point right here, right? This point is p of a 1/2 and a 1/2. Okay? And it's kind of the center point here. And if I put in a 1/2, I get a 1/4, a 1/4, a 1/4, a 1/4. Right? It's the average of all the 4 points. Okay? It's the average of all the 4 points. And if you want to, if you connect this line and the star by a straight line, okay, it turns out that this point here happens to be the midpoint of that line. Okay? Happens to be the midpoint of this straight line. And it turns out that this point here, that's a straight line, folks. Right? Happens to be at the midpoint, and that line there happens to be at the midpoint, and that line there happens to be at the midpoint. Okay? And so Du and Sabin said, there's even an easier way to calculate this, and that's to first calculate the center point, right? And then just take the midpoint of these line segments. Okay, and you've got the Chaikin's points, right, or what we call the Du-Sabin points. Some people do as you go along. So there's lots of ways you can calculate these points. Okay, and what you can do is let it go. Okay, just let it go, and you're off. Okay, well, go ahead.
Won't all the 4 points converge on that center point?
No, because what you're going to do is there could be another big square over here, right? And you're going to have 3 of these points, 2 more of these points over here. You're going to connect them up like this, right? Across, right? Up like this here. Okay, and then what's going to happen is you're going to get new points for this also, right? So this one might come close to that center point eventually, right? But you're going to keep getting this grid, right, no matter what. Go ahead.
You basically answered my question because, yeah, over time in that one midpoint, I think all the successive Chaikin's points lie on those 4 straight lines.
Right. And now, well, what the next thing is, well, I'll go over to this board here, and let's draw out this. Okay, 4 of them. In reality, what you've got is you've got these 4 center points here. And of course, in the limit, what you're going to get here is that this is going to be a parabola, right? Because what Chaikin's curve does is it goes to these parabolic segments halfway in between, right? This one's going to be a parabola, this one's going to be a parabola, that one's going to be a parabola on the outside. And what you get is, what you get in the limit from Chaikin's is you get this bi-quadratic, by 2 directions, bi-quadratic thing, okay, in the limit. Bi-quadratic. Patches, I'll call it sewn together, right? Because there's going to be another one out here, right, etc. in the limit. And so what you're doing is, as Chaikin's goes along, or as Sabin goes along, you're getting closer and closer and closer and closer to these actual patches. Okay? And what we do with these things is, we're off. Right? Let the algorithm go, we start. And actually, this is actually fairly straightforward to implement. Okay? And then they started doing, what they found out though is that you can do this on even a more interesting thing. Okay? So here's another grid. Let's don't do that line. Here's a little bit more interesting grid. Okay? And this grid is not like this grid. I'll talk about how we store this grid in a minute. Okay? But having all these grid with just rectangular quad type things in them all the time turns out not to be very useful. Okay? In general, trying to fit quad things in on surfaces doesn't work a lot of times. A lot of times you end up with little triangles. Trying to fit quads in on a sphere is very difficult, whereas if you start from an icosahedron, right, or something nice off a sphere, it looks really great. Okay? And so dealing with something like this, the question is, what happens if I have something that is a mishmash of all different kinds of things here? And actually, I don't even have one that has 5. I should. But I'll deal with this one, okay? And you'll see what happens. And the answer is, we can do the same thing over here as we did over here if we only do the following. What we do in the case of each one of these things is we calculate the center point, which is the average of all 3, okay? And then we put radial lines to the vertices from the center point, and we calculate the midpoints along these lines, okay? See what I'm going to do? Now this is just like Chaikin's so far, right? Calculating the midpoints of these lines. What gets fun is when I come to here, okay? I calculate the center point, the middle, right? And put midpoints, right? I'm going to get 4 here. Let's speed up a bit. See what I've done? See what I've done? It's pretty simple. All I did was take the center point. Suppose I had a shape that had 6 sides on it. Same thing. You take the average of all the 6. That's the center point. You run these things out, right? And you...
How well does it work if you have a non-convex polygon?
Still works. Yeah. It, again, shrinks away from things, right? So in the case of non-convex, it'll shrink toward your non-convex region, if that makes sense. But still works. Okay? And now you got to reconnect this. Okay? You got to reconnect it to make it work, but it's not too hard to see how to reconnect it. What I do is I connect the dots on the inside. Okay, and then I connect the dots lines across the edges, right? So I get a quad across the edges. Okay. How am I doing? Okay. This is kind of weird. I'm missing something here.
Maybe that's so in that quad, you took the leftmost, you take the one that's top.
There should be a point right there. Like that? No, it's okay. There's always a quad there going across. There. I'm too close to the board to actually be able to see what's happening. I'm probably messing this up. Actually, no, maybe not. Like that.
You did make a pentagon right there, like direct, like almost the center.
There's 2 pentagons.
That's right down.
That pentagon.
All of it, like two things down. Right? Yeah,
Those surround the vertices.
Yeah. Yeah, there's a pentagon here. There should be. Yeah. Yeah, that's the next point of the discussion is that, you know, you don't all get quads out, of course, right? You don't all get quads out when you do this. You get quads across the boundaries. That's okay. Okay, you get quads across the boundaries. You get triangles in the middle that reflect the number of sides the original had. Okay, they get smaller and smaller and smaller, right, as you go along. Around the points here, you get a polygon that looks like the number of edges coming out of the points, right? So there's 5 edges coming out. You get a pentagon, etc. And you know, well, you effectively can see what's happening here. Okay. Now, all I did was the Chaikin's like algorithm, right? I just extended the Chaikin's like algorithm, and the whole key was finding that you know, you get the center point, and then you get the midpoints of the radial lines. You get to the edge points, and it's done. All right, and you can now do it again on this structure, right? And on this structure, and on that structure, and et cetera, et cetera. And it converges to something. Okay. The question is, what does it converge to? And the interesting thing is, mathematically, we don't really know, right? There's no nice mathematical object it converges to, but it converges to something. And you can use this algorithm for spheres. You can use it for all kinds of things, to generate spheres, to generate all kinds of things. Okay? But it's complex. You're getting now out triangles, you're getting rectangles, you're getting these things out. And in fact, in any place here, I don't know if I have such a place, if I do, eventually what's going to happen is the following. This guy is going to continue, there's going to continue to be a pentagon here, okay? But it's going to get smaller and smaller and smaller. There's going to continue to be a triangle here, but it's going to get smaller and smaller. The rest of the world is going to end up being quads when I'm done, because over every edge I continue to get a quad. no matter what. So the rest so I'm going to have these are called extraordinary points in the trade. They're called extraordinary points. Around the extraordinary points, I'm going to get some interesting non-mathematical thing, right? But around everywhere else, I'm going to get quads. And you can see here, 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 here. Yeah, I still get a quad, right? Here, here, right? And maybe here. I'm not doing this quite right. Eventually, we get little 3x3 sets of quads, right? And from over there, we know those are the Chaikin surfaces. So eventually we get these little Chaikin things, okay? But around these extraordinary points, we're not, and these are piecewise quadratic, biquadratic things. But around these extraordinary points, we're in trouble, okay? We don't quite know what we get. We actually know it, we can do it so it actually comes out fairly okay, right?
So once you end up with the actual pentagon, like in the center, that is created by connecting the Chaikin's points that are around it.
Right.
Then on the inside, the next time you do the algorithm, do you count that as a space for calculating the Chaikin curve?
Sure. Well, I mean, but you're still going to get that pentagon no matter what.
Yeah,
okay.
Because then you just shrink the
Yeah, but it keeps shrinking, and around that pentagon you get these little quads all the time. And the little quads, once you get 3x3s, end up being the biquadratic, biparabolic Chaikin's things, okay? But so most of it is a whole bunch of these biparabolic things pieced together, okay? Go ahead.
So do these extraordinary points reflect critical points of the surface?
That's one way of looking at it. Depends on what you call critical points. We can actually calculate at these extraordinary points. We can actually calculate derivatives and things like that. They tend to be. I'll show you. Okay, it'll take me a couple lectures to get there, but I'll show you. Okay. So this whole mess here, okay, you can do. Right. The only problem is, how do you store this thing in a data structure? Right? That thing over there is easy. It's just a 2x2 matrix, 2x2, n by n matrix. Right? This one isn't anymore. Okay? It isn't anymore. Go ahead.
It seems like you have to have, each vertex has to have its own set of vertices that it's connected to.
Yeah. What you've got to say is effectively, I need to somehow, in order to calculate this point here, I have to know, or these points, what these vertices are connected to. Okay. Over there, I know what it is. That's easy, right? You do I plus 1 and I minus 1, j plus 1, j minus 1, kind of to move around this matrix. Over here, you don't have that. You kind of have to have a data structure that does this. And there is a data structure that people tend to use. Most of us call it the data structure from hell, because that's what it is. It's effectively pointer hell. Okay? And this is the way it looks like. I'll draw a pentagon this time. Okay? And what we do is people typically keep something called a split edge. This is called a split edge. Okay? And a split edge has several pointers associated with it. I think I can do with that, with 3. It has several pointers associated with a split edge. One of these pointers here points at the vertex. And typically what we do is we keep our vertices in a huge array somewhere else in storage. And we first put our vertices somewhere else in storage in a huge array, because it doesn't make any sense to store this pentagon, this triangle, this quad, and store that vertex 4 or 5 or 6 times, right? That doesn't make any sense. It makes much more sense to keep your things in a big array and store a pointer toward the vertex. So this guy has a pointer toward this. I'm going to point here at the vertex, but it has a pointer toward the vertex array. Okay? Now every edge is going to have one of these split edge things on it. So there's going to be one thing over here. There'll be one thing up here. one thing over here. And one thing over here. Okay? And each one of these things is going to have a pointer toward the vertex. That's behind it. Okay? Now each one of these things is going to have a pointer to the next one around the edge. Okay, it's called a clockwise pointer. And it points to this thing clockwise around the edge. Okay, and then this one is going to point to, well, there's going to be another maybe polygon over here attached to this one. This one is going to point at the half edge, the split edge that's over here on the other side of this edge that belongs to this polygon. Can you see how these things are all going to link up together now? Okay. This guy's clockwise, this guy goes back. Okay? And you can see that, and also, that, I mean, this gets even more complex. Quite frequently we keep a list of faces for our polygons. Okay? And so these guys typically also have to refer to the face, and the face has to refer to at least one of these. Can you see pointer hell coming at you? Okay? Now, but you can work your way around the edges of a polygon quite easily, right? You can work your way around a vertex. It's not too hard. Starting here, you go to here, then across to here, then to here, across to here, then to here, across and back. So you can work your way around a vertex, right? So those of us that write data structures, we have, most people, have you guys written iterators yet? For data structure, we write an iterator to go around a face, we write an iterator to go around a vertex, okay, etc. And now when you want to, you have to think about pointer hell coming up, here it comes, right? What you want to do is you want to split these, right? So you want to calculate this point, okay? Get these lines. Do these Chaikin's points. Here's your Chaikin's points. Right? Connect them up into another structure. Right? Think about building all these new split edges up. Okay? And you'll eventually be throwing this edge away because you'll have another split edge going across. But this enables you to work all the way around here pretty easily. And we typically have a data structure like this split edge structure to do that. Okay? Now, all of a sudden you're looking like, oh my God, right? And that's what it is. It's oh my God when you code this up from scratch. Because if you have a nil pointer in here, you're dead. Okay? You're dead. And you get just instant seg fault and it's over. Okay? The other thing that's cool about, you can reference your whole mesh by just referencing one of these. Okay? Because we all have algorithms that basically work our way through and kind of let us visit each face, right? You can do this by using, as long as it's all connected up, you can do this. You can have algorithms go through and visit each face. Usually these guys have a mark. I can mark them or so that I visited them or something like this. As we go through, you can go through and look at each face. A lot of times this is why we keep a list of faces. It's much easier to iterate through and look at each face if we have a list of all the faces involved. But the alternative here is that when you first start writing these, if you're naive in writing them, you write a vertex class, you write an edge class, and then you write a face class. Okay? And you say, okay, vertices, right, belong to a whole bunch of edges, so I have to list all the edges. And they also belong to a whole bunch of faces, so I have to list all the faces. The edges belong to exactly two faces, that's okay. I can list the faces. Right? And they belong to exactly two vertices, I can list the vertices. And we're going to actually exploit that a bit tomorrow, or Monday. And then the faces, right, have a list of edges and a list of vertices that I have to look at. And can you see even worse pointer hell coming there? Okay, it's even worse pointer hell coming there, because all these things have to refer to each other, and you have to keep them all updated. And if you miss one update in your code, right, you're dead. And if you really want to, I've actually given this to a data structures class. Right, they didn't like me too much afterwards, but I've actually given this to a data structures class to implement. It's not, it's actually not that bad, and it shows you a lot about some data structures that we might want to do. Now, in that video I showed you with the guy playing chess in the park, right, by himself, his hands were all made of surfaces like this. Right? Actually, not Due-Sabin surfaces, but they'll be Catmull-Clark surfaces, which I'll discuss next time. Right? Catmull-Clark, the difference between Due-Sabin and Catmull-Clark, and it turns out they were both published the same year but differently. The difference between Due-Sabin and Catmull-Clark is that Catmull-Clark is cubic. You get the bicubic pieces. Okay, so each piece is a cubic Bezier patch. Right? Where here, this is you get biquadratic. Each piece here is a quadratic Bezier patch. Okay, and so the rules on Catmull-Clark are a little bit different, but I'll show them to you. Okay, and these surfaces are actually, after you get used to them, they're actually kind of cool, right? But they do take an extra data structure that most people don't provide for you. Okay, they do take an extra data structure, and off they go. So this is the Due-Sabin, Catmull-Clark. This is the introduction to subdivision surfaces. Everybody does subdivision surfaces right now. Everybody does. Okay, and when you do cubics, effectively what we're going to do is we're going to chop corners off things. Okay, we're going to chop off corners, and the nice things are going to be in the middle, and the corners are going to be bad. And we're going to chop corners off things. And also, next time when we get together, I'll show you two things. I'll show you the Catmull-Clark one, which is the one that most people use, and then I'll show you one that works on, I'll show you several that work on triangles. Right? Lots of times when you have these bad surfaces like this, you say, just take the pentagons and everything and make them triangles. Right? Just subdivide them into triangles. And then we'll have these triangle-based algorithms, and we'll let a triangle-based algorithm work on them. And the triangles, they help you a little bit. The pointer hell isn't so bad, okay? But it can still be quite challenging. Go ahead, I had a question.
So what's the advantage to having the quadratic Bezier curves as opposed to the biquadratic patches?
Well, they're both biquadratic. Okay. Well, it turns out the biquadratic things over here are really biquadratic Bezier curves. Anything that's polynomial I can make into a Bezier. They're biquadratic Bezier patches. Okay? And the advantage of using Bezier patches is just they're easy to use. Okay? The nice thing about Bezier curves is in the cubic case we can specify 4 points, right, and we get this nice continuous thing. And we can get any curve, any cubic curve in the world by specifying 4 particular points. Right? For computer scientists, that's cool because we can't store continuous curves. Right? We have a discrete device. This way, we can store 4 points and do it. In the case of a Bezier patch, we can store 16 points. Right? And we have this nice continuous thing underneath. And by moving these points around, we can get any bicubic thing out of it. Okay, and that's what's cool about these Bezier things is you only have to store these few points, right, in order to be able to do continuous mathematical things with them, and that doesn't happen very much in the real world. Okay, the question's here for a long time, and it was solved by this impossible to read paper in about 1998. The question here for a long time is what happens around the critical points? What really happens around the critical points? Is it nice and continuous? Is it, not continuous? What happens? And nobody knew for a long, long time until a guy from effectively Adobe wrote a paper, which still is. It took me only about 3 weeks to understand it. And it's just almost impossible to understand. But it showed that actually things are pretty nice there, right? That we really don't have to worry. And now, if things are pretty nice there, then all of a sudden you can take these things into the engineering world. and start making vacuum cleaners and airplane wings and things like that out of them. And but still, you think of this data structure from hell that has to underlie these things. That when you want to go to these advanced things now, all of a sudden the n by n matrices disappear, and now you have to do some weirder things when you're going. Those of you who take 177 will find that typically you get a big rectangular array of data points given to you, and you want to make a picture out of it. Well, many scientists also do. What if I just have tetrahedra all over the place? Not triangles, but tetrahedra all over the place. How do I do the same algorithms? And the answer is you can do them, but it gets a lot harder. Right? The data structures underneath have to be kind of cool. So, okay, I'm done today. I will see you on Monday. No discussion today, but there will be next week.